Okay, so last time you see we were looking at the modular function lambda, okay, and you know that this modular function is only invariant under the congruence mod 2 subgroup. It is not invariant under the action of a general element of the unimodular group PSL to Z. So we asked the question, what will happen if we apply a general element of PSL to Z. Then we found that this modular function lambda satisfied certain nice functional equations which we derived, okay. So just to put our discussion in proper perspective, see we are trying to get hold of a modular function which is modular for the whole group, the whole unimodular group PSL to Z, okay. What we have at present is the function lambda which is invariant only for the congruence mod 2 subgroup, alright. So the aim is we have to use this lambda to cook up another function which will be invariant under the action of the full unimodular group. So that leads us to study the mapping properties of lambda, okay. So so let me recall among various recurrence relations satisfied by lambda, we have the following. So in particular you see we have we have lambda from the upper half plane with values in C, okay. This lambda is invariant under the action of an element of any element of PSL 2Z subscript 2, okay. This is the congruence mod 2 subgroup, okay. In other words, you see if well A is an element of this congruence mod 2 subgroup, then if I take a tau in the upper half plane and apply A of tau, of course it is going to give me another point in the upper half plane, because after all PSL these are all elements in PSL 2R which are automorphisms of the upper half plane, and then if I apply lambda to this I will simply get back lambda evaluated at tau, okay. So this is the invariance property, okay. So we have seen this, and see in fact we saw, so see we would like to know that if you look at the the complex plane which I will call as the tau plane, and then I take the mapping omega equal to lambda of tau, okay. So this is a mapping that is going to be go into take values in another complex plane which I will call the omega plane, and well we are looking at of course you see for the moment lambda is defined in the upper half plane, alright. So lambda is defined here, this is upper half plane, okay. So lambda is defined in this shaded region, right. So it is defined here, and so lambda is defined here, and you know of course lambda is analytic, lambda never takes the values 0 or 1, okay, and we want to know what is the what kind of a mapping lambda is. Of course you see lambda is it's an analytic function, so it will have good mapping properties, okay, but the question is what are those mapping properties, we need to understand that. So the first thing I want to tell you is that you see lambda, so the first observation is that lambda has period 2. So this is the first observation. See that is lambda of tau plus 2 is lambda of tau for all tau in the upper half plane, okay. The first property is that lambda has period 2. Now how does one see this? Well, you see there are two ways of seeing this. One thing is you see the transformation tau going to tau plus 2, okay, this has matrix, has representative, has matrix representative, well the matrix representative will be, you know, for a general linear transformation a tau plus tau going to a tau plus b by c tau plus d, the matrix representation is ABCD, the matrix ABCD, and of course you always normalize to make sure that this is that the determinant of that matrix is 1, so that it's unimodular, so that it is unimodular, and well this is going to be that way, it's going to be 1 2 0 1, this is the matrix representative, and you can see that this this matrix, if I read it mod 2, it is identity matrix, see which is congruent, which is equal to the, which is I2 mod 2, okay. So this matrix mod 2 is identity, therefore you see this is in the congruence mod 2 subgroup, okay. After all, the congruence mod 2 subgroup consists of all those elements which when you read mod 2 give you identity, okay, that is you have to read every coefficient mod 2, alright. This is in the clearly this matrix is in the congruence mod 2 subgroup, and you know that the function lambda is invariant under such an element. So you see so lambda of if I apply 1 2 0 1 to tau, this is the same as lambda of tau, okay. So of course applying 1 2 0 1 to tau means it means that you are applying the Mobius transformation z going to 1 z plus 2 by 0 z plus 1 to tau, okay. So which means so the left side is just lambda of tau plus 2, okay. So lambda of tau plus 2 is lambda of tau. So so the moral of this story is that if you want, since lambda has period 2, alright, so it's enough to study you don't have to study lambda on the whole, the effect of lambda on the whole upper half plane, it's enough to study it on a vertical strip of length 2, okay. So therefore what we do is that we actually so we do the following, we restrict our it is enough to restrict our attention to this strip. So I will take this strip, so I will take this strip, namely you see I will take this as 1, this is minus 1, okay. So I will take it's enough to study lambda only in this region, the effect of lambda on this region, that will do. It's enough to study the effect of lambda on this cross shaded region, okay. You can restrict to a vertical strip of horizontal length 2, alright. So it's enough to study lambda only here, alright. Now well of course there's also another way of there is another way of looking at it. You can also use the fact, we may also use, so maybe I'll draw a line here. We may also use the functional equation, lambda of tau plus 1 is, I guess, 1 minus lambda of tau. See, we proved this last time. Lambda of tau plus 1 is 1 oh no, I think it was it is lambda tau by lambda tau minus 1, sorry. So that was lambda of minus 1 by tau. Okay, so this is lambda tau by what was that? It was lambda tau minus 1, and now you apply this twice, alright, then you will get, so lambda tau plus 2 will be lambda tau plus 1 by lambda tau plus 1 minus 1, okay, and then you apply this to this, you will get lambda tau by lambda tau minus 1 divided by lambda tau by lambda tau minus 1 minus 1, and you will see that this is again going to give you lambda of tau. Okay, so there are two ways of seeing this, right. Of course, this is very straightforward, right. All right, so the situation is now that it's enough to study the effect of lambda on this region. Okay, then so what is it that what is the kind of result we are going to get? So let me state the result that we will get. It is the following. So let me write the theorem. Okay, so this you see, let me draw this circle here which is centered at half and radius half. Okay, so I get this region. Okay, and similarly I can draw a circle centered at minus half, again with radius half, so I will get something like this. Okay, and let me look at this region. Okay, let me look at this region. Okay, let me look at this region that is bounded by the imaginary axis, by this circle, and by this line which is a real part of tau equal to 1. So you see, this is real part of tau equal to 0. This line is real part of tau is equal to 1, and of course this line is well, real part of tau equal to minus 1. Okay, so you look at this region that I have shaded. I have not shaded it fully, but the boundary is supposed to be consisting of this portion of the imaginary axis followed by this semicircular arc, and then this portion of the line passing through 1, or vertical line passing through 1. Let me call this region, let me give a name to this region. Let us call this region as omega. Let me call this region as omega. Alright, then the theorem is the following. The theorem is lambda maps omega injectively, in fact let me say lambda maps omega isomorphically onto the upper half plane. Okay, so it is very beautiful. So this region you see this region here, this region omega, by omega I mean only the interior of the region, don't include the boundary curve, the bounding curves, okay. So that interior is of course an open set, okay, and the fact is that this open set is completely mapped isomorphically by lambda onto the upper half plane, okay. So the image of that is this whole upper half plane, and the fact is that you see it is the fact is that it is an isomorphic, it's isomorphic, that means it is injective and holomorphic. Of course lambda is of course holomorphic, right. So to prove this you just have to prove that the map lambda restricted to this open set is 1 to 1 and that it takes every value in the upper half plane. If you do that, then you will get this, the proof of the statement. Not only that, of course you know you expect a conformal map when it maps a certain region to a certain region, then it has to map the boundary to the boundary, alright. So the beautiful thing is that this of course you know lambda is defined only for the upper half plane, okay, but the fact is that you can extend lambda to the boundary of this region omega in such a way that you can expect where the boundary has to go. You see the boundary has to go to the boundary, here the boundary is the real axis, okay. So the fact is that lambda can be continuously extended to the boundary so that the boundary of omega goes to the real axis, okay. So let me write that down. Further, lambda can be continuously extended to the boundary of omega, okay, which means you know this portion of the imaginary axis followed by this semicircular arc and then this portion of this line, okay. So that which is mapped onto the real axis, okay, which is what you should expect because the boundary of this region has to go to the boundary of that region, okay. So you see so this whole thing is going to get mapped to the real axis, and which values are going to be mapped to which. So you see lambda, the value of lambda at the point at infinity, okay, will turn out to be 0, okay. So in such a way that zero, so the point at infinity goes to 0, okay. So on this complex plane there is a point at infinity, okay, which you must think of as, you must actually think of this stereographic projection and think of the point at infinity as the north pole, okay. That point goes to actually 0, okay. Then the point 0 goes to 1, okay, 0 goes to 1, okay. This 1 will go to infinity, this 1 here will go to the point at infinity, okay. So you see what is happening as you come from the point at infinity on the Riemann sphere to 0 to 1 and again go back to the point at infinity on the Riemann sphere, what happens is the lambda values go from 0 to 1 to infinity and then back to 0. That is how lambda is extended to the boundary, okay. So this is the theorem, okay. So I mean the importance of this theorem is that because of the behavior of this region under several of those mappings, which were the mappings that you got in the congruence mod 2 subgroup, okay, when you read it in Z mod 2, okay, this allows us to extend, I mean to cook up from lambda a function which is modular for the whole unimodular group, okay. So the key lies in studying this region, okay, the key lies in studying this region, and this region is kind of fundamental for the way lambda behaves, the way lambda maps, okay. So so we will have to prove this. So this is roughly the aim, and in fact I should also say that, you know, I could have also taken the mirror image of this region, okay. I can take the mirror image of this region about the imaginary axis, and you know I will get this region here, okay. I will get this region, alright. Now let us call this region as something, let us call it as, let us say omega prime, okay. The fact is that this omega prime will be mapped by lambda to the lower half plane, okay. This omega prime will be mapped by lambda onto the lower half plane, and again the mapping will extend to the boundary with the same properties, okay. And mind you, the values of lambda here are exactly the same as values of lambda here, because this differs by 2, which is the period of lambda, alright. So what will happen is that, you see, the image of this is going to be this, the lower half plane, you are going to get this, okay. So let me write that lambda also maps omega prime isomorphically onto the lower half plane, which I will call as minus u, okay. So this is u, so this is the upper half plane, this is minus u, this is the lower half plane, okay. So this is how lambda behaves, and of course so the effect of the mapping on these two pieces will give you the full image, and of course you will have to extend the mapping to the boundary, to this boundary, and of course if you have extended it here, it automatically extends here, okay. So you have to only extend it here, right. So well, so this is what we have to prove, okay. This is what we need to prove, and as a first step towards that, you see, so I'm going to try to prove this. So the first thing I'm going to try to show is that that the value of lambda on this boundary, okay, I'm going to show that the value of lambda on this boundary is actually real, because after all, you see what lambda is doing. What lambda is doing is that, you see, it's mapping this whole thing onto the real line, okay. Now so for that, let me again draw the diagram here, okay, and make a certain observation. So here is, so this is 0, this is 1, this is the tau plane, okay. So you have the semicircle here, okay. So you see this is real part of tau equal to 1, this is real part of tau equal to 0, and of course you know this semicircle is mod tau minus half is equal to half. This is the equation of a circle centered at half and radius half, right. Now what you must understand is that, or what we can observe immediately is that you see this imaginary axis, I mean this imaginary axis is mapped by tau plus 1 onto this, okay. So you see if I apply tau going to tau plus 1, this every point here goes to a corresponding point here, alright, and the point in the upper half plane goes to a point in the upper half plane, 0 will go to 1, alright. And notice that we know that lambda of tau plus 1 is, as I wrote it down here, lambda of tau plus 1 is lambda tau by lambda tau minus 1. Okay, so you know what is the advantage of this functional relation? It is if I prove lambda is real on this, okay, if for tau on this, if I prove lambda of tau is real, then this will tell me that lambda is also real on this, okay. So that is the advantage of this functional equation. So lambda real on the imaginary axis implies lambda real on real part of tau is equal to 1, okay. And of course I will have to worry about the point 0 and the point 1, because for the moment lambda is only defined on the upper half plane, okay. So what I am saying here applies only to only when imaginary part of tau is greater than 0, okay. So let me write that down, where imaginary part of tau is greater than 0, okay. So you will have to leave out this point and you will have to leave out this point, right. Then notice also that you see this line is mapped onto this circle by the transformation. So there is a transformation that is going like this, and this transformation is none other than tau going to 1 minus 1 by tau. You see, take the transformation tau going to 1 minus 1 by tau, it is a Mobius transformation, it is certainly a Mobius transformation, and you see, and you know that a Mobius transformation will map straight lines to straight lines or circles, and circles to straight lines or circles, you know that is a fundamental property of Mobius transformations. So you see, if you take this tau going to 1 minus 1 by tau, you see if I put tau equal to infinity, so infinity will go to 1, okay, tau minus tau going to 1 minus 1 by tau, if you calculate this, infinity goes to 1, the point at infinity goes to 1, alright, and then well infinity goes to 1, then if I take the point 1, which if I take the point 1 goes to 0, okay. I mean maybe I should put no, that is alright. I mean I am only worried about this transformation, I am not applying lambda, okay. So if I put tau equal to 1, okay, 1 goes to 0, alright, and then well if I put something in between, say for example suppose I put tau is equal to suppose I put tau equal to 1 plus I, okay, which is this point here, which is this point here, 1 plus I is somewhere here, this length being 1, okay. Then 1 plus I will go to what? It will go to 1 minus 1 by 1 plus I, which if you calculate is it's 1 plus I minus 1, so it's I by 1 plus I, and that turns out to be I into 1 minus I by 2, and this is I plus 1 by 2. Okay, this is, so it's 1 plus I by 2, which is this point. It is half plus I by 2. So you see this Mobius transformation maps infinity 1 plus I by 2 1 to 1 1 plus infinity 1 plus I 1 in that order to 1 1 plus I by 2 0. So you know, so this is the conformality as you go from, as you move from infinity to 1, okay, the image of this line is traces this semicircle in this order. Okay, so you see this is mapped onto this. Now you have another functional equation. The second functional equation that we saw was that lambda of minus 1 by tau plus 1. Okay, this turned out to be, well, if you recall that it is lambda tau minus 1 by lambda tau. We have this, we proved also this functional equation. Now what does this tell you? This tells you that if you knew that lambda is real on this, you can then conclude that lambda is real on this. Okay, so lambda real on real part of tau equal to 1 implies lambda real on this segment, on this semicircle for imaginary part of tau positive. Okay, so you see, to show that lambda is actually real on this boundary, I have to only show that lambda is real on this imaginary axis. Okay, and I have to worry about the point 0, I have to worry about the point 1, that is all I will have to do. Okay, so you see, so the first part of our discussion proceeds to show that lambda is real on the imaginary axis. Okay, so lambda is real on the imaginary axis. So so let me write that down. We only need to to check lambda is defined and real on the boundary of omega, del omega. Okay, we only need to show, number 1, lambda is real on the imaginary axis, we need to show this. Okay, in U of course. Okay, and number 2, lambda at 0, and so like you have to show lambda of 0 is 1, lambda of 1 is infinity, and you know I need to also show limit as tau tends to 0, lambda of tau tau inside omega is 1, limit tau tends to 1, tau inside omega, lambda of tau is infinity. Okay, so this is what I have to show. See, if I show this, So if I show this, then I will know for sure that you see that this boundary is mapped onto the real axis, and that the only true troublesome points are these 2 points, and there those are the points where I will have to check continuity, okay, so that I make sure that the mapping when you extend it to the boundary is also continuous. So I will have to verify these 2 limits as well. I have to check that the limits are these values, and then I will have to verify these limits, okay. So this is going to be the first part of our discussion, right. So how does one go about this? So to begin with, now I need to go back and define a more general Weierstrass free function, okay. So let me do that. Let us recall that you see we need to define a more general Weierstrass free function. We need to do this. So what do I mean by that? So what you do is, well, you fix 2 complex numbers omega 1, omega 2, 2 complex numbers with the ratio with omega 1 of course both not 0 and omega, let us say omega 2 by omega 1 is non-real, okay. That is, omega 1 and omega 2 are linearly independent as elements over R, the real numbers, okay. Then associated with this we will have a lattice, okay. So you get L of omega 1 comma omega 2, this is the lattice spanned over Z by omega 1 and omega 2, and what is this? This is just the Z span, namely it is all Z linear combinations of omega 1 and omega 2, so it is of the form n omega 1 plus m omega 2 where n and m are integers, okay. And of course the lattice that we have been so far considering was L of 1 comma tau, where tau was in the upper half plane, but instead of taking 1 and tau we are simply taking 2 complex numbers such that the ratio omega 2 by omega 1 is non-real, alright. Now if you recall, you take the complex plane and then you go modulo this lattice, okay, namely you declare 2 complex numbers to be equivalent if they differ by an element of this lattice. In other words, you are thinking of the lattice as the group of Mobius transformations that act by translation by elements of the lattice, okay, and then you are going modulo that group. What is the result? The result is again a complex holomorphic torus, it is a Riemann surface, okay. So what you get, so this what you get here is the torus T sub omega 1 comma omega 2 is a complex torus, okay, and of course you will see that the way we got the Riemann surface structure on this torus was such that this mapping pi is a holomorphic map, and in fact this mapping is a holomorphic universal covering for this torus, and the fundamental group of this torus can be identified with the lattice above as the deck transformation group of this covering, and the deck transformations are precisely elements of the lattice being thought of as translations on which are automorphisms of C, okay. So this is the picture, and again see our aim is to get hold of a simple function on this, the simplest possible analytic function on this. Of course you will again not get an analytic function on this because this is compact, any analytic function on this will be constant. So you will see that you will have the simplest function you can think of this will be a meromorphic function, okay, with which will show up as a meromorphic function above, which is invariant under the lattice, under the translations by the lattice. It will have a double pole just like the phi function that we saw for the case when this was 1 and that was tau. It will have again a double pole at each point of the lattice, okay, with residue 0, okay. And again what happens is that you will get a vs phi function. Let me call this as phi sub omega 1 comma omega 2, and this will take values in C union infinity. This is the Riemann sphere. This will be the Riemann sphere, and of course it will go down to give you you will get a function here which is the simplest meromorphic function you can think of on a complex torus, okay. Now and how do you define this p sub omega 1 comma omega 2? It's the formula is literally the same as the formula that we used to define the phi function when omega 1 was 1 and omega 2 was tau. So the formula is pretty the same, pretty much the same. So you see phi sub omega 1 comma omega 2 of z turns out to be 1 by z squared plus summation omega varying over this lattice of omega 1 comma omega 2 omega not equal to 0 1 by Ez minus omega the whole squared minus 1 by omega squared. It is the same, it is literally the same of the same form as you as the phi function we defined when omega 1 was 1 and omega 2 was tau, okay. So phi tau of z is just phi, in this notation it is phi 1 comma tau z. The original the function that we defined earlier is just phi 1 comma tau. You take omega 1 as 1 and omega 2 as 2, okay. Then again you can see that the arguments that we had for p tau of z about its properties will all hold for this, okay. And in fact again just like p tau of z satisfied a differential equation, this will also satisfy a differential equation, alright. So what will happen is that you will get this will satisfy the differential equation so that's the same, it's literally the same differential equation that we had earlier, and that's going to be, well, p phi prime squared is equal to 4 phi cube minus g2 phi minus g3. You are going to get the same differential equation, okay, where of course this phi is phi sub omega 1 comma omega 2. You are going to get the same differential equation, and you can continue to factorize it as 4 times phi minus E1 into phi minus E2 into phi minus E3, and to determine what E1, E2 and E3 are, we look at the zeros of phi prime, and you find that E1 is actually phi of omega 1 by 2, E2 is phi of omega 2 by 2, and E3 is phi of omega 1 plus omega 2 by 2. You get all these things, alright, and the arguments are exactly the same as they were when omega 1 was 1 and omega 2 was tau, okay. You can try writing that out as an exercise and you will see that literally the same arguments do it. Alright, now well the advantage of this is that I can I mean the advantage of all of this is that I can replace omega 1 by 1 and omega 2 by minus tau where tau is in the upper half plane. Okay, see in the original phi sub tau that we defined, tau was in the upper half plane, so I couldn't replace tau by minus tau, because if tau is in the upper half plane, minus tau is in the lower half plane, and I have not defined the phi function when tau is in the lower half plane. Okay, so it is only to overcome that difficulty that I am looking at this more general phi function. Okay, now what I want to tell you is that so I want to tell you that if you now look at these functions yes, so what I want to tell you is that I just want to say that if you now put omega 1 equal to 1, okay, and omega 2 equal to tau, but now do not assume tau to be just assume tau to be imaginary, non-real, okay, assume it to be complex, not real, so it could lie in the upper half plane or it could lie in the lower half plane, then these three become functions of tau on the which may lie either in the upper half plane or in the lower half plane. Alright, then I want to say that these three as functions of tau, they are real on the imaginary axis. Okay, so you see, so let me write that down. So you see, E1, note that E1 is actually a function of omega 1 and omega 2, that is, I mean each of the EI's are a function of omega 1 and omega 2. Okay, so the E1 is phi, so from here onwards phi is actually phi sub omega 1 comma omega 2. Okay, see the phi depends on omega 1 and omega 2. Alright, so E1 is this phi of omega 1 comma omega 2 evaluated at omega 1 by 2. So what you must understand is, though I write E1 is phi of omega 1 by 2, you should not misinterpret it to think that E1 depends only on omega 1, E1 also depends on omega 2, similarly E2, E3, so all the A's are functions of both omega 1 and omega 2. Alright, now see the fact is if tau is if tau is purely imaginary, okay, if tau is purely imaginary, that means either tau is in the upper half plane or and in the on the imaginary axis, or it is in the lower half plane and on the imaginary axis. Okay, then the EI of tau are all real, or they are all real value, then these EI's are all real value. Okay, and what is the proof for that? So let me take let me compute so but before this I need to tell you, I need to ask you to put omega 1 equal to 1, omega 2 is equal to tau, which is not an element of which is not real. Okay, so put omega 1 equal to 1, put omega 2 is equal to tau, which is where tau is not real. Okay, and then the fact is if this tau the tau may, see tau is not real, so it could still have a real part. Tau is not real only tells you that it has an imaginary part which is not 0, okay. It could have a real part. If further that real part is 0, that means that is the case when tau is purely imaginary, then I say that Ei of tau are all real valued. So you see, so when I write Ei of tau, now it is really a function of only tau, because the only variable here is tau, alright. Now let us calculate this. For example, what is E1 of tau? E1 of tau is by definition P of 1 comma tau of 1 by 2, this is what it is by our definition, okay. And you see this is what is this? This is by our definition it is 1 by 2 the whole squared plus summation over omega in the lattice generated by 1 and tau, okay, omega not equal to 0, 1 by 2 minus omega the whole squared minus 1 by omega squared. This is what it is. This is what E1 of tau is. Now you see, calculate E1 of tau conjugate, okay. Calculate E1 of tau conjugate. The E1 of tau conjugate, if I take conjugate on this side, if you watch, this is not going to be affected. If I take conjugate here, you see what is going to happen is that this omega is going to be replaced by its conjugate, okay. So what I will get is I will simply get 1 by 2 the whole squared plus summation over omega in L 1 comma tau, omega not equal to 0, I will simply get 1 by half minus omega bar the whole squared minus 1 by omega bar squared, this is what I will get, alright. Now you see that if tau is purely imaginary, then tau bar is minus tau, okay. So what you will see is that you see that this will be the same as this, okay, which will tell you that therefore that E1 of tau is real if tau is purely imaginary, okay. So because you see what is omega bar, see omega bar will be an element of the form n plus m tau, I mean omega will be an element of the form n plus m tau, therefore omega bar will be an element of the form n plus m tau bar, okay. So you know this can be written as 1 by 2 the whole squared plus summation over omega belonging to L of 1 comma tau. So now you see I replace omega bar by omega. If I replace omega bar by omega in this summation, I will have to replace tau by tau bar, alright. So I will have to put tau bar and I will have to put omega not equal to 0, and I can write the same old expression. I can now write it as half minus omega the whole squared minus 1 by omega squared, I can do this, okay, because I have replaced omega by omega bar, and replacing omega by omega bar is to compensate for that I will have to replace tau by tau bar. But you see tau bar, you see if tau is imaginary, tau bar is minus tau, so L of 1 comma tau bar will become L of 1 comma minus tau, but the lattice generated by 1 and minus tau is same as the lattice generated by 1 and tau. So this will be simply equal to E1 of tau if tau bar is equal to minus tau. So the moral of the story is that if tau is imaginary, then if tau is purely imaginary, then E1 of tau is real, alright. So from this it follows that lambda is real because lambda was cooked up from these things, okay. So let me write that down. So this is this should be. Thus E1 of tau is real if tau is purely imaginary. Okay. Similarly, E2 of tau, E3 of tau are real if tau is purely imaginary. Okay. So this implies that lambda of tau, which was defined to be E3 of tau minus E2 of tau by E1 of tau minus E2 of tau, this is how lambda of tau was defined. This turns out to be real if tau is purely imaginary. Okay. So this completes the proof of this statement that lambda is real on the imaginary axis. Okay. So this is the next statement that one has to prove, and I'll do that in the next lecture.